Continue our discussion about the subspaces. Recall that last time we defined what is the sum of arbitrary family of subspaces. So, let us recall it. Let as usual K be a field and V be a K vector space. For a family, for an arbitrary family, UI indexed by the set I of K subspaces of V, the smallest subspace of V containing all UIs exist, and it is called the sum of the family UI, usually denoted by sum I in I UI. This is also one can describe element wise. This is nothing but all finite linear, not finite sums where J is a finite subset of I and each xi belongs to UI for I in J. So, we have seen last time that the right hand side is a subspace. That just follows from the subspace criterion, because if you have two finite sums, then the sum of that is also finite sum. Also scalar multiple of a finite sum is a finite sum. So, that means this right hand side is a subspace, and it is clearly it clearly contains all the UIs, and it is clearly the smallest one. So, therefore, by definition these two subspaces are equal. Okay. So, in particular, let us understand for finitely many subspaces. In particular, when I is finite, let us say 1 to n, and we have a family, we have n subspaces U1 to UN, K subspaces of V, then the sum U1 plus U2 plus UN is the subspace of the sums x1 plus xn, where x1 is in U1, xn is in UN. This is the smallest subspace of V which contain all U1 to Un. Okay, so let's continue. I want to give couple of remarks. So how do we construct from a finite family of vectors? So let xi I in I be a finite arbitrary, actually I do not want to take finite, be an arbitrary family of elements. Remember, we are also calling elements of a vector space as vectors in V. Then the smallest subspace of V which contain all xi's. This means that is the smallest subspace of V which contains all subspaces k xi I in I, because if it contains all xi, then it contains all subspaces, cyclic subspaces generated by the xi's. So this is precisely this notation kxi I in I. This is precisely finite sums J in J, finite AI xi, AJ xj, such that AJs are some elements in K, xj's are among the xj's, and J is a this is J in J, a J is running over finite subsets. Such a finite sum is also called K linear combinations. So this subspace, the subspace kxi I in I is called the subspace generated by the family xi. So any element in the subspace generated by this family is precisely a finite linear combination among the x's, and the family xi I in I is called a generating system of the subspace this. Obviously, V is generated by all of its elements. But it could also be generated by a proper subset of V. However, V may be generated by proper subset of V, or even be finite subset. So, formally, if Xi is a generating system of V, then V is the smallest subspace of V containing all Xi's. In this case, V is K Xi I in I. This is useful for checking whether a system of elements is a generating system of V or not. Okay, so just to give one example, let us take our model example of a vector space V equal to k power n. This is also, I just want to remind you, can think of them as maps from 1 to n to k. These are n tuples. So, in this you have these E1, EI, EI is 0, 0, 0, ith place 1 and everywhere else it is 0. This is the ith place. This is also denoted compactly by delta ij, 1 less equal to j less equal to n, where delta ij is the standard Kronecker symbol. Then we have these n vectors E1, E2, En. Obviously, V is generated by E1 to En. So, we need only to check that every element of V is a linear combination of this E1 to En. So, that will mean that V is the smallest subspace which contain all these guys. So, for this, note that any tuple which is A1 to An is same as A1 E1 plus A2 E2 plus 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 an en, where these a1 to an are elements in the field. This is obvious because you see when you want to check that the two tuples are equal, you have to check that all coordinates are equal. So for example, a1, this is the first coordinate on the left hand side. On the right hand side, the first coordinate is only contributed from this term, because all others e2 etc. up to n have no first coordinate at 0. So when you multiply this, and our vector space structure is component wise addition and component wise multiplication, so this is obvious. So this checks that a1 to E1 to En is a generating system for the vector space k power n. Also note that fewer elements will not work. No, we cannot drop any one of E1 to En to get a generating system. That is obvious, because if you, for example, if you drop E1, then you can never get E1 as a combination of E2 to En, because all E2 to En have coordinates, the first coordinate 0. Okay. More generally, you can generalize this example. More generally, if you take V to be k power round bracket I, where I is an arbitrary set. Let me remind you, k power round bracket I is precisely, this is the set of all I tuples with coordinates in k and almost all coordinates are 0. So formally you can write like this: this is ai, I in I, ai are in k, and ai equal to 0 for almost all I in I. Remember the phrase almost all means all but finitely many. It doesn't mean infinitely many. Okay. So in this case we can continue denoting the same way: ei for each I in I, ei is delta ij. This is varying in j in I. Again the same Kronecker symbol. So though it looks a infinite tuple, though it looks a tuple indexed by I could be infinite, but in this tuple really only finitely, only one is non-zero, namely I equal to j case, j equal to I case. So then the family of these vectors ei, I in I is a generating system for the vector space k power I. Again for this, like we have noted in a finite case, just note that if I take any tuple ai, I in I, in k power round bracket I, then this tuple ai is nothing but summation I in I, ai, ei. Note that the sum on the right hand side makes sense because only finitely many ai could be non-zero. So, note RHS makes sense since AI equal to 0 for almost all I. So, okay. So, for the future use, I would like to formally write linear combinations. We have seen if let xi I in I be a family of vectors in V, then the elements of the subspace sum kxi are of the form summation ai xi I in I, and now I can write this ai I in I it belongs to k power round bracket I. That means this sum is really a finite sum. This is called these elements they are called k linear combinations of the family xi. So, for calculation we will often if I have one k linear combination ai xi and another one. So, this means first of all ai should belong to k power round bracket I. Do not forget this round bracket, that is very important because we need only finitely many AIs could be non-zero, not more. And another one bi xi I in I with bi tuple also the same k power I round bracket. Then there is sum this is by our rules distributive and rearranging the brackets and so on. This is nothing but the sum I in I ai plus bi. This is where we are using the vector space rule. Remember the first lecture, 4 properties those. So, and note that again this tuple ai plus bi tuple they are added in k by using the addition in k, and they will also have the property that only finitely many components are non-zero. Similarly for the scalar multiplication, a in k, a times ai xi I in I this is summation ai xi. I could write a bracket here, I in I, and ai belongs to k power round bracket I. So, in case I is a finite set, say 1 to n, then we have only finitely many elements in any k linear combination of x1 to xn. So, these are n elements in the vector space, is of the form. Now, we can afford to write it explicitly a1 x1 plus an xn, where these a1 to an, they are n tuples. Okay, so I would like to end this section. Okay. I would like to discuss one example, couple of minutes. So, one example. Very important example, and I will keep using it many times in various arguments. So, it says that if V1 to Vn are subspaces of a vector space V, and all of them are proper, each Vi is a proper subspace. If K has, the field K has at least n elements, then the union can never be V. Note that here I should remind you, note that the union of subspaces need not be a subspace. Simple example, for example, if you take V equal to R2 and take two subspaces, V1 is x axis, so that is tuples of the form x comma 0, x is varying in R, and V2 y axis, that is 0 comma y varies in the real numbers. So, pictorially it looks like this. V is R2, so it's a plane. This is V, and V1 is this axis. This is V1, and V2 is y axis. So, if it is a subspace, if the union is a subspace, then for example, one element here and one element here we could add it, but that will be this element, which is obviously not in the union. So, therefore, union is not a subspace, and this checking in this example I will leave it as an exercise. Remember, K has at least n elements is very important condition. Without that, this will not be true. Okay. We will take a break and then continue.